Let's try to quickly summarize what we've done in the last series of clips. We asked what's the surface area of a sphere, x squared plus y squared plus z squared equals 16, confined to the first octant. I say above the first octant, that should probably say in the first octant, but let's not worry about that. So the first octant picture looks something like this. We have a typical delta x, a typical delta y, a typical delta A region in the xy plane, and the region that lies above this region. We can go through the reasoning with a sample point xi star, yj star, our partition of the x and the y intervals, let's say our partition of the x interval, and then the resulting partition of the y strip from whatever our xi star value is out to the curve in the xy plane. Our z value here will be square root of 16 minus xi star minus yj star, xi star squared minus yj star squared. We'll have a slope in the x direction, which will allow us to sketch, this side of the region on our surface. A slope in the y direction. Those two slopes go together to give us vectors tangent to the surface, and by taking the appropriate cross product or by considering the angle of the normal vector with the z direction with the k vector, we find that the area ratio is square root of 1 plus fx squared plus fy squared. We haven't gone through the details here. And that means the ratio of the area on our surface that's projected above, that projects onto this region here of our xy plane. So the function, rather the surface area of the sphere in this octant, is therefore represented by the integral of the function whose graph is the surface, z equals square root of 16 minus x squared minus y squared, obtained by solving this equation for z. That'll be our f of xy function. That function is integrated over this region of the plane down here, that region being x squared plus y squared less than or equal to 16, with also the proviso that x and y are both greater than 0. This and or our consideration of the partition, how the y limits are dictated by the value of x, gives us this description of the region, x going from 0 to 4, y going from 0 to the square root of 16 minus x squared, leading us to the integral you see here, integral from 0 to 4 with respect to x, 0 to the square root of 16 minus x squared with respect to y of this area ratio. This integral represents the area of small region of the xy plane multiplied by the ratio of the area of the surface to the area of that increment. In terms of this function, f of xy equals square root of 16 minus x squared minus y squared, it's easy to calculate fx and fy. Just briefly, fx is going to be the derivative of the inner function x squared 16 minus x squared minus y squared, that derivative with respect to x, times 1 over 2 times the square root of 16 minus x squared minus y squared, giving us for this function fx equals negative x over this square root. The y derivative is very similarly seen to be negative y divided by the same square root, so that our expression 1 plus fx squared plus fy squared becomes 1 plus x squared over 16 minus x squared minus y squared plus y squared over the same denominator. Putting all this over common denominator, 16 minus x squared minus y squared, we see that the 1 becomes 16 minus x squared minus y squared over 16 minus x squared minus y squared, and now we can add the other two terms and we get this result. Our x's add up to 0, our y's add up to 0, so that our area ratio 1 plus fx squared plus fy squared just reduces down to 4 divided by the square root of 16 minus x squared minus y squared. Fairly simple form. We check to make sure the area ratio is greater than or equal to 1, as it must be. The area of a region above the XY plane has to be at least as great as the area of that region. And we verify that, well, X and Y are both greater than 0, greater than or equal to 0, so this expression is less than or equal to 16, meaning its square root is less than or equal to 4, meaning we're dividing a smaller number into a larger number. Our area ratio does end up being greater than or equal to 1. So, with this expression for our area ratio, we can write down our integral, the same integral we have here, just plugging this expression in here. We find that our integral is the integral that you see here from 0 to 4, 0 to the square root of 16 minus x squared of the area ratio multiplied by the dy dx. And we're left with the task of integrating this thing. Now, this thing can be integrated, and it's really not too difficult using trigonometric substitution, but we're going to have to do that with the x and with the y. If we're a little bit clever, we'll notice that the x squared minus y, negative x squared minus y squared, could be the negative of our polar coordinate r squared, so that if we can change this integral to polar coordinates, we might have an easier time with the integration. Well, here's what happens when we change to polar coordinates, but I've written it out a little more completely here. Our motivation for changing to polar coordinates is that 16 minus x squared minus y squared becomes, through an intermediate step, 16 minus r squared. Our region, 0 less than or equal to x less than or equal to 4, 0 less than or equal to y less than or equal to the square root of 16 minus x squared. And that inequality can be easily read off of these limits on the integral, and also comes from our geometric model, the intersection of the sphere with the first octant. That region, since the upper limit on y is 16 minus x squared, that means that at the upper limit, y is the square root of 16 minus x squared, which is easily rearranged, square both sides, etc., into y squared plus x squared equals 16, circle of radius 4, with a center at 0, 0, so that this region clearly becomes this region, where r goes from 0 to 4 and theta goes from 0 to pi over 2, so that in polar coordinates, here's our region. Our integral can therefore be written in polar coordinates very simply. Theta goes from 0 to pi over 2, r goes from 0 to 4, and our expression 4 over the square root of 16 minus x squared minus y squared just becomes 4 over 16 minus r squared. Our area increment is r dr d theta, and recall how that comes out of the Jacobian, how that was derived simply by the meaning of the partition and the dimensions of a typical increment of the partition. We end up with this integral, collecting some terms, bringing the 4 out in front, putting the r over the 16 minus square root of 16 minus r squared. We obtain this expression for the surface area of that sphere in the first octant. This expression is easily integrated. Let u equal 16 minus r squared, du is negative 2r dr. We have the r dr here, so that our r dr becomes negative 1/2 of the du. And our integral is, well, we write out the integral again. Here's the integral. We write it out here. We repeat what we just said about the u and the du. And it doesn't look like I wrote it out, but let's just very quickly write out that r dr is negative 1/2 of a du, so that this integral can be rewritten in this form. We've made the r dependence of the limit explicit here because we had the alternative of using U limits or retaining our R limits, with the idea that once we have an antiderivative, we're going to switch it back to our switch our U back to our 16 minus R squared. So the integral becomes this and is easily integrated. Essentially, all we need is the fact that the integral of U to the negative 1/2 is 2U to the 1/2. We put that in to this expression and we get this. Our limits are still R limits, so we're going to change our U back to 16 minus R squared. Our U to the 1/2 becomes this. We substitute our limits. We be careful. We make sure to take care with our signs and our plus and minus signs, and we get this result, 8 pi. We re-emphasize that this is a surface area of a sphere of radius 4 in the first octant. Should be 8 pi. The surface area of a sphere is 4 pi r squared, where r is its radius, so that if r equals 4, the surface area is 64 pi. The first octant is 1/8 of our three-dimensional space. The sphere is symmetric with respect to the origin in three-dimensional space, so its surface area should be 1/8 the surface area of the entire sphere, and that's the case. 1/8 of 64 pi is certainly 8 pi.